This video abstract is AI generated. Nanoparticle sedimentation is a major obstacle for solution NMR studies of adsorption. During the long experiments needed to detect weak ligand nanoparticle interactions, particles settle out of the NMR active volume, and the sample is no longer homogeneous. As a result, the spectra become difficult to interpret, and quantitative surface contrast NMR measurements are compromised. We previously solved this problem in water by suspending nanoparticles in agarose gels, but many ligand nanoparticle systems of interest are studied in organic solvents, and agarose cannot be used broadly under those conditions. In this work, we set out to extend surface contrast NMR to non-aqueous environments. Our solution was to build an organogel platform based on low molecular mass organic gelators. We screened a library of 48 gelator solvent combinations to identify matrices that both stabilize nanoparticles and preserve detectable ligand surface interactions. The key challenge is that the gel itself can broaden NMR signals, so we developed a simple screening strategy based on proton R2 measurements. A useful organogel should produce a small change in ligand relaxation in the absence of nanoparticles, but still allow a clear relaxation increase when nanoparticles are added. In other words, the gel should not dominate the line broadening, while nanoparticle adsorption should remain detectable. Using this framework, we examined phenol with cerium oxide nanoparticles in non-aqueous media. Several organogel systems preserved the phenol spectrum while still allowing the adsorption-induced broadening to be observed. We then applied the same logic to cholesterol with cerium oxide, showing that the approach also works for a larger and more complex ligand. Together, these results show that organogels can prevent nanoparticle sedimentation in organic solvents while maintaining the NMR sensitivity needed to detect adsorption. This expands surface contrast NMR beyond aqueous suspensions and provides a practical route for studying nanoparticle interfaces in a much wider range of chemical environments. To know more, read our work online.